Okay, hello everyone. Welcome back to my YouTube videos and welcome back to my videos on power system analysis. As you must be aware, I am creating a series of videos called Introduction to DC Transmission Systems, and this is the part 2 of that series. Today the topic will be HVDC technologies. Okay, if you are familiar, HVDC technologies is something that is coming back to the market quite strong in the previous 10 or 15 years. Okay, and I would like to clarify that I will try to go for the most popular and commercial technologies here. Okay, there are some experimental technologies or some technologies that are still in the labs, and I will not cover them here. Okay, if you are watching this video, it's because probably you are already subscribed to my YouTube channel. However, if you want to be registered at my Twitter or LinkedIn, I will be extremely happy to having you over there, and also all the slides and numerical examples, you can download them from my GitHub. Okay. Let's go for business. What is the agenda for this video today? The agenda is a quite long agenda. I will start with a comparison between the HVDC systems and the classical HVAC systems. I mean the comparison between direct current and alternate current used for high voltage transmission. Okay. Then I will go and talk about some applications of HVDC systems inside the power system, and an introduction about HVDC and the basic concepts related with converters. And then I will go for a very short introduction about commutation techniques used in HVDC system converters. Okay. Again, I would like to clarify, if you are a power electronics enthusiast, this video is probably not the best for you. Okay. The approach used in this video is mainly from the power system point of view. As a consequence, I will not go in full details inside the converter. Okay. However, as power system engineers, you must have a proper understanding about some implications related with something happening inside. One of them is the commutation. Okay. Then I will go through several of the different type of converters, starting with the line commutate converters, then go for the capacitor commutate converters. Then I will talk about the force commutate converters, and finally I will make a comparison between the LCC line commutate converters and the voltage source converters VSC. Okay. Finally, a very brief and very short explanation about multi-level converters. It's probably the most recent technology. There are many topologies, there are many concepts that I will not cover here, but I will give you the brief introduction that you need for a basic understanding. Okay. Then I will go across some HVDC transmission system configuration, monopolar, bipolar, and multi-terminal, especially multi-terminal using bipolar converter stations. Okay. Then there is a short summary, and finally some references. However, you must be aware that I am using many sources here. Okay. Regarding these resources, I would like to say that this presentation was created probably 7 or 8 years ago, and it's been evolving And as you can see, there are many links and many sources, and the references at the very end, they are not probably the full list of references, okay? And also I try to put as much as I can references inside the document, and please forgive me if I forgot to put the credit of somebody else. It's not related with plagiarism, it's probably stupidity that I forgot to include some references, okay? Well, let's start from the very beginning, a comparison between HVDC systems and HVAC systems. The classical comparison between AC and DC, okay? And I will start with something very simple. As you must be aware, transmission systems, they are created to move power between two locations or multiple locations. What I'm trying to say is that the original idea of using transmission system is to move very high power or a lot of power inside the power system. That is what we call bulk power, okay? And imagine that we have the following problem. Imagine that we need to think about technical alternative when we are talking about transmission power, transmitting a lot of power, okay? Here, as you can see on the top, you can see the high voltage AC alternative, and over here down you can see the high voltage direct current alternative, okay? Of course, when we are talking about AC, we are talking about three-phase systems, okay? And for that reason, you can use high voltages or ultra high voltages or extra high voltages, 500 kV. That is a logical decision when we are working with high voltage bulk power transmission, or 750. In some countries, almost they reach 1,200 kV. Okay. However, one of the situation when you are using a very high voltage for transmission is that the transmission line in AC has a big capacitance, and these big capacitance make the voltage control a real problem. And that is the reason that is quite typical that if we are working in extra high voltage or ultra high voltage, you will find many compensations. I mean, reactive power compensation, and that is one option. I mean, using using HVAC systems from 500 kV until 1,200. But on the other hand, we can use a direct HVDC system to move a lot of power, and over here you can see that if we need to transmit a lot of power, several options are available. 500 kV bipole, 550, 600, or 800 kV bipole. I mean, you have positive and negative bipole, and you can use those big elements, okay? However, if you look this table on the right-hand side, and you can see here the comparison, okay? For instance, if we are trying to move 1,000 megawatts using AC, we can use a single transmission line of 500 kV, but the transmission distance should be between 300 and 500 kilometers. If we use a bigger, a larger, a higher voltage, for instance, in this case, we are talking about 1,000 kV, okay, we can reach a bigger power, 5,000 megawatts, but the distances increase to 1,000 or 2,000 kilometers, okay? What I want that you start to understand is that AC systems have limitations. And one of the limitations is related with this capacitance that we are creating when we are using extra high voltages and very long distances, okay? However, look over here. If we are using HVDC solutions, using 500 kV, we can transmit easily 3,000 megawatts at distances from 500 kilometers to 1,500 kilometers. I mean, as you can see, with lower voltages, we can transmit more power. And also, if we go to the biggest voltage, for instance, here I have 1,100 kV. If you look over here, we can reach 11,000 megawatts. That is something that is not doable using AC transmission system. I mean, it can be done, but you need 3 or 4 transmission line, very big transmission lines, and also the voltage regulation will be a bit of a nightmare, okay? Here, from the very beginning, what I would like that you understand is that DC systems are more efficient in terms of transmitting a lot of power for very long distances, okay? And they are extremely useful because there is no problem related with capacitance, and for that reason, voltage control is easy compared with AC systems when we are using extra high or ultra high voltage, okay? In this slide, the next slide, what I am trying to show you is, coming back to the same problem, imagine that we would like to transmit 2,000 megawatts or 2 gigawatts. 2,000 megawatts, and there are some options over there. We can use a bipole of 500 kV, plus minus 500 kV DC. And you can see here on the extreme left, the simple and beautiful transmission tower over there, okay? And as you can see, something that is extremely important when we are using transmission, when we are creating transmission lines, is what we call the road, the right of way. The right of way is the land that is immediately underneath of the transmission line, below the transmission line. And that 50 meters, for instance, for this 500 kV, you say 500 meters is not so much land, but if we are talking about 100 kilometers transmission line, you can multiply 50 meters, multiply by 800 kilometers, and you will get a massive amount of area that you need to buy in order to get the right of way for this transmission line. What I'm telling you is, if we have a small right of way, we need to spend less money for the right of way, and as a consequence, the transmission line, the cost of installing and the cost of this transmission line will be reduced. On the other hand, if you look over here on the right hand side, that is the solution, technical solution for 200 megawatts transmission. We are talking about 2 transmission lines, 2 with 500 kV. You can see over there, there are 2 towers, and because you need 2 transmission lines, as a consequence, you need a right of way of 110 meters. That is almost a bit more than the double that we can need, or that we need if we are using a DC transmission line. What I'm trying to say is that the DC transmission lines, they are compact, and especially because we are using DC, the distances are shorter, because the difference in the electric and magnetic field, okay? I will not go there because that is not my job. But what you need to understand is, for the same amount of power and the same distance, the use of HVDC is better for long distances, okay? Here in the middle, you can see the beautiful 800 kV AC solution for 2,000 megawatts. And as you can see over there, even using a single line with 800 kV, we need 85 meters of right of way, okay? That is a lot of land. From now, you can start to see, okay, there are few problems, there are few things related with the use of AC. Voltage control, one of them, and also the right of way, okay? Well, here you can see the progression of the AC voltages, okay? Here I am showing, this is a plot where you have here the rate voltage on the vertical axis, horizontal axis presenting years, and as you can see over there, we are using 1,200 kV, okay? It's already, and the voltages has been increasing, but there is no, as you can see over there is no a jump of after 1100 or 1200 kV. I mean, the distances that you need in order to keep safe distances between conductors, that is extremely large. And as a consequence, the cost of transmission line with even bigger or larger, higher voltages, it's more expensive. Okay. But I don't want to talk bad about AC. Okay. AC has been in the electrical power utility for many years, probably more than a century. But we need to recognize the following: AC has limitations. Okay. AC have many limitations. Okay, I don't want to talk about I don't want to talk bad about AC system, but we need to recognize that there are limitations. One of the most powerful and most important limitations is the distance limitation. Okay, the distance limitation is something that is related with the power carrying capability of the AC line. Okay. What I'm trying to say is that the power that we can move using a transmission line, the capacity is inversely proportional to the distance. I mean, if you start to increase so much the distance, the power that you can move from one side to the other is less and less and less. That is something coming from the static operating limit of the transmission line. And that is not happening on DC transmission lines. If you are using DC transmission lines, it's virtually there is no limit for the use of DC. The only limit is probably a technical limit or economical limit related with the voltage drop or the cost of the structures, but there is almost probably no limit using DC. Okay. And regarding AC lines, as I said before, when we are using extra high or ultra high voltages, the effect of the capacitance to ground or the grounding wires, that effect start to create a big capacitance, and also the capacitance between conductors, okay, phase conductors, and these big capacitance start to be a problem because the voltage is producing that those capacitance have some currents going through, and that is what we call the charging current. The charging current is the current that a long line with a lot of capacity is requiring from the system, even if there is no load. I mean, it's something similar to the exciting current in a transformer. The charging current is the current that is going to the capacitance through the capacitance in the transmission line. And for ultra high voltage or extra high voltage, those capacitance can be extremely high, and those charging currents can be a problem. And there is a reason that we use compensation. Okay, we use reactive compensation. And also because we need to keep control about these voltages during the operation of the power system, and that system and that condition, you must recognize that the controllability of the voltage require the use of dynamic voltage compensation using reactors. Okay. Another interesting problem, another interesting thing is that when we are using AC transmission lines, when we are using the classical AC, the connection create a synchronous connection. I mean, from one point of view, that is quite interesting, because from one point of view, all the systems share the frequency, and the frequency is moving through those AC cables. And for some purposes, that is quite good. I mean, everyone having the same frequency. But one advantage of the HVDC system is those converters, they are taking AC signals and converting into DC. And if those converters are appropriately located, they can create an isolation in terms of synchronism. That can create an isolation in terms of synchronism, or what we call a synchronous connection. And on the other terminal, we use the DC and convert and then go back to the AC system. But the interesting thing is, in this conversion, AC to DC, DC to AC, we can have more controllability. We have probably full controllability of the power that is moving through the transmission line, the DC transmission line. And that is something that is not easy if you are using AC signals. If you are using AC signals, controlling the power that is going through a transmission line is a bit more complicated, because you need to move the angles, and that is not something that is not easy, or changing the reactance or the impedance of your transmission line, and again, is something that is not easy. HVDC, they have the possibility of a synchronous connection, and also that allow more controllability of the frequency and the active power in AC systems. I don't know if you understand the asynchronous connection, but one very interesting example that I will be talking about is the interconnection between Brazil and Paraguay. Brazil, Paraguay, they have different frequencies. If you have a country with 50 and another country with 60, there is no possible way that you use a transmission line for interconnection, because you have two very big different frequencies on the extreme terminals or the connection terminals. And that is impossible, because you will never synchronize two systems with two different frequency. The only solution, using HVDC, decoupling the frequency, and that was the reason that Itaipu in Brazil, they have this back-to-back converter and HVDC transmission system in order to interconnect two systems with different frequency, okay? Okay, I was talking about the frequency that we want to know. The frequency is moving inside the AC system. But the frequency moving inside the AC system sometimes is good, because allow you to have a proper control of the power system. But if you have bad oscillation, if you have a cascade event, that cascade event will move through the whole power system, and then you will have a problem, because the frequency or the power oscillation will propagate for the whole AC systems. On the other hand, the HVDC systems, they are like a barrier, like a firewall. When you have oscillation, we are talking about frequency oscillation or power oscillations, and they reach the converter. Okay, on the other side, on the DC side, this frequency variation, this power variation will not go through to the other side. Okay? Okay. Now, I was talking about some limitations of HVAC systems, the AC systems, against the DC systems, okay? And over there, you can see on the right-hand side, there are a very interesting plot, and this plot is quite interesting, because in that plot, the horizontal axis is dedicated for the transmission distance in miles, okay? And the vertical axis is the maximum loading that you can install in the transmission line. And here you have a very interesting comparison. The three lines on the top, 345, 500, and 765 kV. But that is AC, okay? And I don't know if you can see here, but you can see the yellow starting from very high, and then start to going down around 600 miles. It's the same here with 500 kV AC, and blue, that is the same for 345 kV. But if you look here, those colors, the light blue, the purple, and the red, you can see that those are three plots representing 500 kV DC, 660 kV DC, and 800 kV DC, okay? And over there, what you can see is that DC, the limit, the transmission distance limit, of course, is not changing so much for the DC system. In theory, it should be a flat line, but in reality, there are losses and there are other things. And however, it will be never comparable with the AC system, okay? What you need to understand is something quite interesting. AC has some limitations, and one of the limitations is coming from voltage stability. The voltage stability limit of the transmission line that is defined basically in terms of the magnitude of the voltage and angle at the terminals of the transmission line, okay? Okay, of course, we can try to increase those stability limits and mitigating the problem using, for instance, several lines in parallel, or start to install flexible AC transmission system called FACS, using HVDC, static voltage controllers, and so on, okay? Or even synchronous capacitors, okay? However, the problem, the issue related with the distance, the transmission distance of AC systems, is mainly related with the reactive power related to the transmission process, okay? And what you need to understand is AC lines, they have a limit on the distance that they can transmit power, okay? On the other hand, we have the DC lines that there is almost no effect related with distance, okay? When I was talking about the reactive power, I believe you can see here this other plot, and that other plot is related with the reactive power that we need for different voltage levels. And as you can see over there, if we are using 765 kV and the distance is very short, we need some reactive power, negative reactive power, but we start to go for 400 or 4,000 miles. You will need more compensation, and when you increase also the power to 4,000 megawatts, the requirements that you will have in terms of reactive power increase, okay? Coming back to my DC systems, they are not limited, or the limitation is so high that we don't consider that no distance limitation for DC transmission line, okay? And also there is not distance that affect the stability in terms of voltage or angles, because there are no voltage or angle when we are using DC systems, okay? Another thing is if we are using DC systems, we don't have intermediate substation. It's not like the AC system, that if we have 800 kilometer transmission line in 765 kV, we need to have intermediate substation, especially for including some reactive compensation and keep control of the voltage, okay? And there is no increase on the reactive power demand, because we are using the DC system, okay? Here in the next slide, I have something similar to my previous plot. Here you can see what is the maximum transferable power that you can obtain using a transmission line, and based on the distance, okay? The horizontal axis is basically kilometers, and the vertical axis is per unit, referred to the transmittable power, okay? And as you can see over there in greenish color, we have few DC lines starting from 80 kV and going into 320 kV DC. And in dark color, you can see here, starting from light gray until something that is probably dark gray, 400 kV AC. You can see in this region, they are limited on the distance that they can transmit power, okay? And that is one of the issues. One of the issues is DC systems, they have almost no limitation for the distance that they can transmit power, okay? However, there is something that is quite important when we are working in projects related with HVDC and transmission systems. One important variable is the distance. And it's very important, that distance, the transmission distance, because the total cost of transmitting power depends basically in two important things, okay? the total cost of the installation, okay, and also the total cost related with the exploitation or the use of that transmission line, okay? I know that people from business and from financial point of view, they will start to talk about variable cost, fixed cost, and so on. Here, I just explaining this very basic, okay? To be honest, I will not go so in detail. I will take just those lines here. In red color, we have the total DC cost, and the blue line represent the total AC cost, okay? I don't know if you realize that the horizontal axis is distance. That means this region over here means short distance, and over here in this area we are talking about long distances. Okay. What I need that you understand is from this point to this point here, I mean in this area, the blue line is below the red line. That means that the total AC costs are lower than the total DC cost, okay? But there is a distance where those lines, they intercept, and that is what we call the break-even distance. The break-even distance means that that is the point that using AC or using DC, the cost is the same. I mean, that is the point that if you use one solution or the other solution, well, the cost is the same. That is what we call the break-even distance. But from the break-even distance onwards, I believe you can see that the blue line starts to be on the top of the red lines. Or what I'm trying to say is the total AC cost is larger than the total DC cost. If you now think about the implications of this, that means that for short distances or distances below the break-even distance, the most economical and technical solution is the AC transmission. But from the break-even distance onwards, the most economical solution for transmission is using DC systems, okay? That is the basic explanation over there. Now the question is why the HVDC cost is higher for short distances and smaller for long distances, okay? Well, that is related basically with the initial cost of the installation and also with the losses during the operation of that system, okay? However, I will talk that in the next slide, okay? Another remark that I would like to say is for many years or decades, the DC transmission line has been used for transmitting power, a lot of power, to long distances, because the break-even distance was very, very large. If there are many papers, there are many publications that they show recent calculations of the break-even distance, and the reality is that in the recent time, the break-even distance is reducing. Why is reducing? Well, one of the reasons is especially the cost of the converter station. I mean, the place when we have the conversion from AC to DC, the converter stations, the price of those converter stations has decreased a lot in recent time. And also the efficiency of those devices has increased. And that is one of the reasons, that DC start to be more popular for shorter and shorter distances, okay? Over here, I have a comparison on the cost structure when we are talking about transmission using AC or DC. Okay, as you can see over here, if you are talking about terminal cost, okay, a transmission line is extremely low. Okay, why? Because in AC, you go from the transformer, go to some circuit breakers, then you connect your cables, go to the towers, and you have a transmission line. But in HVDC system, the history is a bit more complex. You go from the transformer, then you need some filters, you need the converters, you need some or more filters, and then you will go to the transmission line. For that reason, the terminal cost, I mean the cost related with the installation at the substation, is still high on the HVDC. But if we go for two more things, one of them is the cost of the line cost. HVDC require less cables. Let's start from there. If you are using a three-phase line, you need 3 conductors. But if you are using a DC line, you need 2 conductors. 1 conductor is less for the DC systems. And 1 conductor is not just the wire. It's also all the mechanical support, the isolation, and all the components related to that wire. That means that from that point of view, from the line cost point of view, HVDC system is still more attractive. And as I showed you before, the right-of-way cost is smaller when we are using DC systems. And the reason is basically because you have more compact towers, you have shorter distances in that transmission line, and as a consequence, the right-of-way, the cost of right-of-way is smaller. Okay? Okay, what is the conclusion? Well, the conclusion is HVDC is it's cheaper for transmission line for transmission distances that they are quite long. Okay. However, the break-even distance is reducing, and if the capitalization of losses and right-of-way costs are included in the cost comparison, the break-even distance is further reduced. Okay. And we are talking about here classical transmission lines, overhead transmission lines. But if we are talking about subsea cables, wow, that is another history. Because if you are using subsea cable for offshore wind farms, for instance, and you are using AC, well, you need to have some reactants to control the voltage, to keep control of the voltage. And those reactors will be located at the offshore platform. And over there, every kilogram that you add, that is a lot of money. For that reason, for some specific application that we will discuss later, especially the offshore, it's quite interesting the use of HVDC, okay? Over here, there are some numbers. And as you can see over here, the break-even distance start to go to 100 or 90 or 100 kilometers, okay? And that is especially when you are talking about offshore connection. Offshore connections is basically using undersea cables. And those undersea cables, they tend to have much more capacitance compared with the classical transmission lines, and as a consequence of this capacitance, voltage control is more complicated, and DC come to help us. Okay, now let's talk about applications of HVDC systems. Okay, where is the most suitable application for HVDC systems? Okay. Well, HVDC systems can be used for many things, okay? The main application for many years has been the use of pull power, transmitting a lot of power, very heavy loads for very long distances, okay? However, in recent time, advances on undersea cables and the cost reduction of the converter station are making more and more attractive the use of the undersea cables, and also for underground cables on land, okay? And that is another application, quite used application, okay? As I say before, if you have two different systems with two different frequencies, that is a asynchronous interconnection that can be done only using HVDC systems. However, in recent times, HVDC systems using more advanced control and more advanced power electronics, they have include more controllability into the power system. And controlling the active power moving, or the power moving through the transmission line, we can make many things, and one of them is congestion control, congestion relief. I mean, controlling the load flow, you can reduce the congestion or the bottleneck in some specific places inside the power system. And that is when I start to say HVDC systems, they are not coming to overtake the power of AC systems. They are coming to help and to improve the AC system, okay? And there are many range of powers and voltages that we can use for HVDC systems, okay? We can use 500 kV, 600, 800, and right now their installation are also above 1100 kV, okay? Here I have a graphical representation. I have the graphical representation of the three basic or more used range of applications of HVDC, okay? As you can see over there, one application is when you have the DC link inside the embedded into the AC network, okay? What is the reason? Okay, there are many reasons, but one of the advantages of having this is that in the AC system it's very difficult to control the load flow. Believe it or not, it's more complicated than the DC system. For that reason, if we control here the power that is moving through the DC link, well, we are relieving some congestion or reducing some congestion inside the AC system. That is one of the advantages of the DC working embed inside the AC system. However, over here on the left-hand side, you can see two different power systems, AC system 1, AC system 2. They can have different frequencies if you want, because there is no problem. There is no problem that they have different frequencies. They can be asynchronous interconnection, because the DC system will isolate both of them. Or it could be the case that we have two power systems, but they would like to have a firewall between one and another, and the firewall is coming from this DC interconnection. For instance, this is a very interesting case. That is the case of the GB. I mean, Great Britain could be, you can think about Great Britain like the AC system 1, and you can imagine continental Europe as the AC system number 2. They have the same frequency, yes, of course, but we have the HVDC system like a firewall. If something happens, something wrong happened on the frequency on the continental Europe side, the DC interconnector will not allow that the GB system will see that frequency deviation, because there is a firewall, and that is the interconnector, the HVDC interconnector, okay? That is one of the applications when we want to interconnect synchronous or asynchronous system, okay? That interconnection could be using a cable, undersea cable. It could be done using a HVDC transmission line, or also just two converters connected a very short distance. And that is what we call a back-to-back converter, okay? Back-to-back converter is typically used when we don't have any distance between the two converters. We have AC rectification going to DC, then from the DC side going to the AC side, or inverter action, and that is a back-to-back converter, okay? Recent time, the technology related to undersea cables, and also the improvement of the power converters and the commutating devices, that has made quite attractive the use of DC links for transmitting power from offshore wind farms, okay? I believe you must remember my talk about the wind farm in Germany, the Wind 1, and they are using a HVDC system. There are many reasons for that. One of them is that you have more controllability regarding the load flow. And you can control also a lot the voltage in both sides, okay? Now I will show you a couple examples. In Great Britain, we have many interconnectors. HVDC interconnectors, okay? And over here there is an older list, but you can see over there several of those interconnectors interconnecting with Ireland especially, but I would like to talk about this West Link, okay? The West Link is interconnecting Wales with Scotland, and it's basically an undersea interconnection, okay? Why this interconnection is so important, okay? Because this interconnection, you can see here, there is an undersea cable, but that was the alternative, the technical solution, instead of using AC transmission lines over here. I mean, between Scotland and England, we have a corridor, two corridors using 400 kV lines from the north to the south. And creating another transmission line here on land, it could be, from the economical point of view, from the technical point of view, a bit challenging. One solution that National Grid, as system operator, they decide is the use of this beautiful interconnector, the Western Link, 2,200 megawatts. But also the important thing is that this is a classical example of an embedded transmission line. And in an embedded transmission line, if you have the control of this DC power, of course you have the possibility of controlling something that is the power flow inside the 400 kV network. And that was the idea. The idea was not changing the corridor that we already have, but increasing the transmission capacity from the north to the south for more than 6 gigawatts from the north to the south. And it was the shorter solution and also the less expensive, okay? But there are another interconnectors in England. If you look over here, again, I have GB here. This is Scotland, England, Wales, and there is an interconnector going to Ireland, okay? The Republic of Ireland. And you don't confuse this one with this one. The Republic of Ireland, the capital city is Dublin, and the other one is Belfast. Okay, the Northern Ireland. Okay, that is part of the GB, and this is the classical East-West interconnector. The East-West interconnector is again a HVDC system. This case is 500 megawatts interconnecting Great Britain with Ireland, okay? And the idea of this interconnector again is like a firewall, but is allowing the power interchange between Ireland, that is a very wind resource rich country, and the GB system that has more inertia and more controllable generation, okay? And here there is another example. I think we talk about Borwind Alpha, and this is Borwind Beta also, that there are some HVDC systems that they are collecting the electrical power from several wind farms, offshore wind farms, using undersea cables, okay? And finally, from Borwind Alpha, we are going to Germany, continental Germany, using basically undersea cable, 125 kilometers, okay? But 125 kilometers using HVDC is not a problem. But if you try to do something like that using AC, it's quite complicated in terms of voltage regulation, okay? Over here, there is more details about the other three stations that we have, converter stations that we have on the North Sea in Germany. And you can see over there the Borwind, the Dolwind, and the Dolwind 2, okay? Almost to close this, over here, I would like to show you in light blue color over there, I am presenting 9 different areas that we already have offshore wind power, or we are estimated to have offshore wind power over there in GB, okay? And over there, you can identify very big wind farms like Dogger Bank or Hornsea, and we are talking about clusters of wind farms reaching 3,000 megawatts, 2,000 megawatts, okay? And the use of HVDC systems, undersea cables, that will be a key element to consider for the technical solution and the integration of those offshore wind power, okay? And here on the left-hand side is just to present you one of the challenges, but already partially solved, and that is the prototype for the medium voltage DC circuit, okay?